Hello, AP Psychers. Mr. Galusha here with our look at 1.3, the experimental method. We're going to go through a lot of terms. There are things that you're going to have to not only be able to identify in a multiple choice question, but definitely have to deal with on a free response question. That means your level of understanding needs to be at the ability for you to use and explain and not just to identify. So today is definitely a day you want to plug in. Okay, so let's take a look at our kind of basic setup of an experiment. We start with a hypothesis. In this little example, we're going to look at if caffeine is going to make you perform better on your tests. So here's our hypothesis. If a student takes caffeine, then they will perform, their academic performance will be better. Okay. Now I have to have an operational definition for both of these. So we create an operational definition for our caffeine. That's our independent variable. That's the variable that we are going to be giving and seeing if it has an impact. So my operational definition will be the amount of caffeine in milligrams. I don't want to test it in milligrams and have the next researcher test it in grams and not have our two things be the same. So I'm going to define this as the amount of caffeine in terms of milligrams as measured by milligrams. Academic performance is a little harder to measure. We don't have ready set things like grams and milligrams to measure it with. So I'm going to measure academic performance based upon a grade on a test. So I'm going to give students a certain test and then see how they perform on it. And their score on that is going to be my operational definition for their academic performance. So maybe it'll have some ELA stuff, some math stuff, and a whole bunch of psych questions. Okay. So I've made my two operational definitions. Now, which one's my independent? Which one's my dependent? My independent is the one that I'm giving them and I'm testing out to see its effects. Okay, so I'm really curious about caffeine here. And I'm really curious about caffeine's effects on academic performance. That's my dependent variable, is my academic performance. It's the one I'm going to measure. I'm going to measure it by giving them the test. I want to see the impact that my independent variable has. Does it change my dependent variable? And then I'm going to look at my outcome. And I'm going to reject or accept my hypothesis. All the while, I need to be careful not to be biased towards the kids that aren't getting the caffeine. I don't want to give off signals that the caffeine is super important. Those signals would be called demand characteristics. So this is our basic setup. We're going to get into all of this today. Okay, a little more complicated as we look at our basic setup. So I've got my hypothesis. If students take caffeine, then they will perform better academically. I've got my operational definitions, caffeine measured in milligrams. My operational definition for academic performance is going to be their score on a test. Now I've got my independent variable. Okay. But I can't just give everybody the caffeine, right? So I got to give my experimental group the caffeine, and I have to give my control group nothing. Nothing has to change in my control group. How do I decide who goes in each group? I have to randomly assign them. This one over here, but it has to be random. So the easiest way, and what I want you to say on the FRQ, alphabetical list, every other person gets put into the experimental group. That way you've randomly assigned them. Okay. Again, don't be biased. Don't give off any clues. That's demand characteristics. If we have the participants not know which group they're in, it's single blind. If the researcher in the room, not the head researcher, but the researcher in the room doesn't know who has the caffeine, the experimental group, and who has nothing, the control group, then that will be double blind because the participants and the researcher in the room doesn't know. If the researcher in the room doesn't know, they can't give off the clues and they can't be biased. So you eliminate experimenter bias and demand characteristics, a great thing to do if you're designing an experiment. So let's get into each one. Okay. So why do we do experimental research? We do it so we can show a cause and effect relationship. Boom. That's it. We've just come from correlational stuff. That's shown us a relationship. Now we really need to see if there is a cause and effect relationship between two variables. The good thing about experimental research, you allow yourself to see that causal relationship. Your independent variable, caffeine in this instance, or any drug or treatment you're giving, is going to cause a change in another variable, your dependent variable. The weakness would be confounding variables. We'll want to talk about those, any changes that happen between your control and experimental group. Experimenter bias, demand characteristics, but there are ways to wash all of these out. So experimental research really is the very, very best thing that you could possibly do if you're able to do it. So independent and dependent variable. If that term is still not sticking with you at the very beginning, your independent variable is the cause of this. It's what you're studying, caffeine in this instance. It's the variable that you're going to manipulate. And when I say manipulate, we're going to give it to one group and not give it to the other. It's the variable that I, independent variable, starting with the letter I, change. So that might be a way for you to think about it. The dependent variable, this is the one that's going to be affected. Okay, it's dependent on the independent. That's why it's called that. This is the one that you're going to measure the outcome on, and it's going to depend on the independent variable that you are changing. So let's look at it in a real study. There's going to be a statistically significant difference in graduation rates of at-risk high school seniors who participate in an intensive study program as opposed to those who don't. The independent variable, the treatment, the one that I'm going to give some and not give some, is the intensive study program. Some are going to get it, some are not going to get it. That's my independent variable. The dependent variable, the thing that I'm going to see if it has an impact on, is going to be the graduation rates of at-risk high school students. So the graduation rates is my dependent variable, thing that I'm measuring to see if it has been impacted by those intensive study programs. Now, if you get caught up in this and it's just never been your thing since sixth grade, sometimes a hack that you can use is what follows the if is the IV and what follows the then is the DV. If you get confused on that, the if starts with I and so does the IV. So that can kind of help you. It's not perfect. You're not always going to get an if-then statement, but sometimes it can help. Now, we've talked about this so much. Every time you've got your variables, caffeine and academic performance, you have to create the rules that you're going to use to measure them and get a number that allows people to replicate your study. It's absolutely essential to be clear, and that is your operational definition. Please, if you get an FRQ, your variable is going to be a phrase, academic performance, and your operational definition is going to be the rule to get the number, so a score on a test. Make sure you don't get those two confused. One's a variable, one's an operational definition. Okay, use control and experimental groups when you're giving treatments. So if you're giving a drug trial, like the COVID vaccine, if you're doing school programs like we just used, if you're administering, one group eats and one group doesn't, if you're giving some kind of a treatment therapy method, then you need a control and an experimental group. You need a group that gets it, the experimental group, and a group that doesn't, the control group. The experimental group gets the treatment, the control group does not. So in our example, the experimental group is the group that gets the caffeine. They get the independent variable. They actually get it. They take the caffeine, probably in tablet form, right? Like it wouldn't make sense to have them drink. That would be not controlled enough. So they get the independent variable. But your control group still has to take something. Why? Because you don't want any differences aside from the independent variable between the two groups. If the experimental group is taking a pill and putting it in their mouth, it might be the pill. It might also be their belief that the pill works. So what you have to do is give your control group the experience of taking a pill or getting a shot, whatever that thing is, so that they are the same as the experimental group and possibly thinking this is going to work. Think about it this way. If you gave a 7-year-old you were babysitting decaf coffee, but told them it was caffeinated, it's highly likely that 7-year-old is going to act hyper because they believe the caffeine is going to get them hyper. Well, you have to make sure that both groups have that belief, so that the only difference is the actual caffeine. Okay, that's the placebo effect and why we give a placebo to our control groups. So you have the caffeine tablets, you have the placebo. They're both taking a tablet. They both have that belief, that baseline belief, possibly, that this is going to impact their test performance. The difference, the only difference, is the actual presence of the caffeine. And that's going to allow you, as the researcher, to claim that it was the caffeine that made the academic performance better. Now, in a controlled experiment, the control group is the group that does not get the independent variable. They get the placebo and nothing else. It is very important for us to again remind you that it is essential to randomly assign people into your control and your experimental groups. How do I do this? Again, an alphabetical list. Every other name goes on the experimental side. The other names go in the control. Please, 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 please get this down right now. Random assignment is used for assigning participants into control and experimental. Random selection is different. Random selection is when you are selecting people randomly from a population to go to your survey. Assigning someone versus selecting someone into your survey is different. If I'm assigning, I'm putting you into groups. It's used for experiments, control, and experimental. Selection is used when I am selecting who's going to do my survey. If you get these two confused, the College Board will not score your answer correct, no matter how right you are in talking about how you randomly assign or select. So if you're going to get confused on this, selection starts with S, and so does surveys. Okay, assignment and E, A and E go together. So for your knowledge of who has the experimental and the control substance, you can use a single blind or a double blind. Single blind is the participants are unaware of the group they're in. A double blind is the experimenter in the room with them is blind. They don't know if they're actually giving a placebo or the real drug. Obviously, another researcher knows. Everyone's numbered and they're tracked. And the good thing about this is if it is double blind, then the researcher can't give off clues, little hints, subconsciously that they might give off. And it really stops you from having those experimenter biases and then giving off those clues about how people should act, which is called demand characteristics. So again, a single blind, the participants don't know, but the researcher does. Double blind, both the participants and the researcher doesn't know. Okay, probably the most important term in all of experimental design is confounding variables. These are things we don't want. We don't want these. These are variables that a researcher fails to control for or to eliminate. These are things that are different between the experimental and the control group. Now, the only thing that should change is the independent variable. If anything else changes, it could have been the independent variable that had the impact, or it could have been one of those confounding variables. If there were confounding variables, it might have been those, or it might have been the independent variable. We don't know. So let me give you an example of this. Okay, we got a control group, we got an experimental group. The control group doesn't take the drug, and the experimental group takes the drug. Let's say you're a bad researcher and you didn't do a placebo. So the control group takes no pill, and the experimental group took a pill. Maybe the control group took it at night, and the experimental group took it in the morning. See how there's differences between the two? Maybe the control group did not eat breakfast, and the experimental group did eat breakfast. Maybe the control group then went ahead and had coffee, and the experimental group didn't. There's all these tons of differences. At the end of my experiment, I can't just say, oh, it was definitely the drug, because maybe it was the fact that the control group didn't eat breakfast. Okay, so maybe I can eliminate that, okay? But maybe it was that the control group took it at night. Well, maybe I can eliminate that if I keep them. So do you see how this list has to be just drug or no drug? If it's drug or no drug, if it's just the independent variable that was different between the two groups, then I can say it was that. If there's a list of differences, confounding variables, that I didn't make all the same between both groups, then it could have been the drug, or it could have been the fact that these guys had coffee. If there's any differences, I have to be really honest about those and be like, well, it could have been my independent variable, the presence of caffeine, or it could have been something totally different. One of these things. They didn't eat breakfast that impacted their academic performance on the test. So if you have any confounding variables, you really can't make a claim about your independent variable. Again, demand characteristics are things that I give off. The signals the researcher gives off. Take this drug will help you would obviously be a ridiculously biased thing to say. You probably wouldn't see that in real research, but I want you to understand that like maybe this is the therapy method, and the researcher knows that one person's getting a placebo and one person's not. And let's say the person doesn't want to take the placebo, they might fight differently if they knew about it. So demand characteristics are the things that the clues you give off about how the participants should respond. Experimenter bias is any error in your research study due to the predisposed notion or beliefs of the experimenter. So if you point your research in a certain way, that's experimenter bias and would be something that would obviously cloud the results. Okay, that is our rip-roaring good time through experimental research. Get those down in your notes, and then we're going to be applying those the next time we see each other. Take care, AP Psychers.